So we're going to go ahead and start with our last talk for this session. Very important side note. Earlier, someone left a phone on the ground in the back. If you're looking for it, it's sitting up here. Don't come up during the talk. Come up after the talk. But here, we'll move it over here, and if nobody claims it shortly, we'll pass it off to Lost and Found. So for last talk today, we're going to introduce Jeff Fisher from DataKen Research. He is going to talk about automating various things in your home with Python. If you've ever seen that scene in Home Alone where Kevin has to try and make it look like many people are there, I think we're sort of automating that process, which would have saved him a lot of time and effort, fending off Joe Pesci. So, with that, here we go.
Oh, thanks for the great introduction. Can everyone hear me? Okay. So anyway, the topic of my talk is Internet of Things, Python and machine learning, from chips and bits to data science. So we can take you all the way from the hardware level up to data science. And as you said, I'm Jeff Fisher. I'm an independent consultant based out of Sunnyvale, California. Okay, so this talk is about an end-to-end project I did, and we won't be predicting the stock market. We'll just be predicting what your lights would be like in your house if you had been home when you're not home. So we'll talk about that. So I'll give you an overview of the project. Then I'm going to talk about the hardware we did and a little bit about hardware. Then go through the phases, data capture, analysis, and then playing the lights at the end. Some parting thoughts. If we have time, I'll do a little demo. I have one of these boards here, so I can do a live demo maybe. If not, you can find me after the talk if you're interested. Okay? So before I start on that, the question is, why Python for the Internet of Things? Because when I think of Internet of Things, kind of before I started this, I thought of C programming and embedded systems, and not really high-level languages like Python. So we certainly would like to use Python because it's high level, easy to prototype, easy to explore ideas. If you have some hardware hooked up to your thing, some sensor, and you want to do bit twiddling, it's nice to be able to use the Python read, eval, print loop REPL to do that. So it's certainly a nice language for exploring and doing things. But Python actually runs on embedded devices, but depending on your definition of embedded device. So the Raspberry Pi, was started as a project for kids to use as a personal computer, but it has if you can look at it has all these I/O ports here. These things are I/O interconnections called GPIO, or general purpose I/O. So you can hook all kinds of sensors and actuators up to your Raspberry Pi. And the Raspberry Pi is really a Linux workstation. You can run kind of the full data science stack pretty much on a Raspberry Pi. So you can run pandas, you can run NumPy, you can run scikit-learn all on your Raspberry Pi. It may not be as fast as like a desktop or server, but it'll still run there. So this is great. You can take anything you were doing in normal Python, run it there, and you have access to all these sensors and things. And so there's lots of projects that have been done. There's a huge hobbyist community around Internet of Things on Raspberry Pi. And it's even been used in industrial contexts as well. So you can get industrial versions of this and do the same thing. The only downside is it's not battery friendly. So if you want to do something where you want to do some remote sensing, let's say you're in a field somewhere and you want to sense some data of some sort coming from sensors, temperature, light, whatever, you're probably going to need a car battery to power this thing. You're not going to be powering it off of a couple AA batteries. So that's a challenge. But for a lot of applications, you're doing in your house, it's still very, very usable for that. So another thing we can do is there are smaller chips. So like this ESP8266, that's a mouthful, but it's a chip that it was originally designed to be used as a Wi-Fi modem. And it has a CPU, and it has a Wi-Fi radio, and it has a bunch of I/O ports. So it's great for kind of doing IoT things. It has low power consumption. It's easily a 20th of what you would get on a Raspberry Pi, and you can get it lower by playing games with putting it into various sleep modes. So this is great. Now, it has a downside too, which is you only have 96K of memory. And that's not gigabytes, that's not megabytes, that's kilobytes of memory. So that's not a lot of memory. You're not running your Linux there, you're not running your SciPy on there, you're not running CPython on there, right? So you're not going to be doing a whole lot on this machine. Luckily, there's something called MicroPython. And this is an implementation of Python 3 for embedded devices. And MicroPython uses a lot less memory, and it runs directly on the hardware without an operating system. And it even has its own little file system that runs on the flash, but it's very lightweight and has been ported to a number of embedded devices, including the ESP8266. And the other thing I should mention about the ESP8266 is that it's cheap. So this particular board, it's a kind of fancy one. I got it from Adafruit, and it was about $16. But there was, in the Lua programming language community, they were interested in this kind of thing. So they developed a spec, and there's been a lot of implementations of it. And you can buy some of these, it's called Node MCU. You can buy them on Amazon for about $8. If you're willing to wait for shipping from China, you can buy them from China directly for about $4 each, and sometimes even as low as $3.50. So they're really cheap. If you screw up something, it's not a problem because you just pull out another one. So anyway, that's what we'll use. We're going to use both of these in this project. And finally, I just mentioned, Python has a great data analysis ecosystem. That's what the whole conference is about. And being able to kind of write your event processing code in the same language that you do your data analysis in is very, very helpful and makes it a lot simpler process. Okay, so motivation for the project. First, I thought about doing a smart thermostat and controlling my air conditioner and heater. But then I thought, maybe that's too dangerous. I don't know, for my first IoT project, I want to be, having a major repair bill or dealing with high voltages. So I thought lighting is safe. I can't, hurt anyone with lighting, hopefully. So then what do I do? So the idea, and this was actually my wife's suggestion originally. I don't know how well that picture shows up. But if you're out of town for the weekend, like I am, because I live in Sunnyvale, you don't want to leave your house dark, right? It just kind of invites people, is advertisement to people who might want to break in and take your electronics. And even if that wouldn't happen, it's kind of for peace of mind. You want to make it look like people are there. And so we want it to look more like this, maybe not all the lights on all the time. We'd like them to kind of go on and off like people were in the house. And so you can get timers you can buy, at Home Depot or whatever, and you plug your light into it. It has a couple buttons you push, and if you can figure out how to program it, hopefully you programmed it right, and you're always fooling with that right before you leave. And it's kind of annoying, and they're predictable. They go on at 8 p.m., they turn off at 10 p.m. Someone watching your house more than one night will see that it's on a timer. Or they just look, oh, it went on at 8 p.m., not 8:01, right? And we'll see that kind of real usage of a house is a lot less predictable. So I want something that's going to replay the lights that make it look like someone's there, and it's kind of much more random. And I want a self-contained solution. I don't want to involve third-party equipment that someone could brick when they go out of business or get bought by a big company. And I don't want to involve the cloud because that's a security risk and a point of failure, right? So I want it to be all self-contained. And wouldn't it be cool to use machine learning, right? So, okay, so here's the application I came up with. The first part of it is the data capture, and this is really a phase of the project. So first I put light sensors around the house. The remote nodes are using these ESP8266s. Then at my server is the Raspberry Pi. And so that's hooked into my network. And so for 6 weeks, and it was not a continuous 6 weeks, but over about 6 weeks, I captured data from light sensors in my house so that I knew when people were home, what the usual patterns were. So then the second phase is I take that data and I do an offline analysis, and I do it all in a Jupyter notebook. And so it's really convenient using the whole data science stack and kind of understanding what are the patterns, and then I want to come up with a machine learning model that I can use for the player. So the last part is the player, and when you go production, then that's all you need. And I don't want to fool with wiring, so they have these nice smart lights, and what you do is you just wire them, put them in your existing light sockets, and then there's a REST API you can call and you control the lights. So that's the whole system, and then, like I said, all you really need when you're kind of in production is the player. So now let me talk about the hardware. So this is what one of the ESP8266 boards looks like. You see in the back, this white thing is a breadboard. That makes it easy to plug in different components. It has some connections on the back. And so you don't have to do any soldering. And it's good if you don't want to full soldering, as well as if you want to play around and change things. You know, you want to add new things to your board or whatever, or reuse the parts for other things. When you see there's kind of two circuit boards on this, those are called breakout boards. And the reason we have breakout boards is in the old days, kind of when I started as an electronics hobbyist, they had these things called dual inline packages. If you open up an Apple II, you see those chips. Those were easy to work with, but now they have surface mount technology, which are all those flat chips. And as a normal human that has big fingers, those are really hard to work with. They're designed for printed circuit boards. So some of these companies like Adafruit and SparkFun, they've created these breakout boards which incorporate a number of these surface mount things, and they provide easy pins on the bottom that you can hook wires up to and things. So that's what I used. So the one, I guess, on your left is the light sensor. And so that has a light sensor chip and some support circuitry, and will generate a digital signal that can be read by the server board. So the processor board has an ESP8266, as well as an adapter to talk to USB and a battery adapter. So you can power the board through the USB, or you can power it from the battery and you can charge it. And the USB also has a serial port, so that, I don't know if you saw us fooling with it before the talk, and maybe I'll demo it afterward. But you can basically get the Python REPL that's on this board in your terminal on your laptop. So pretty easy to do. And this is the circuits. This is all the connections logically that I have. So you see at the bottom there, basically the power is coming from the processor board, or the ESP8266 board, and that's providing power to the light sensor board. And then there's a digital circuit protocol called I2C, which is used for connecting various peripheral chips, and the light sensor board is using that. And there's also support for that on the ESP8266, and an API for it in MicroPython. So all I have to do is hook up two wires. The SDA is the data. It's basically passing one bit at a time in serial fashion, and SCO is a clock signal. So if you hook up these four wires, and just about anyone can do this, then you have the sensor board. So the Raspberry Pi, I've taken those pins, and I'm using this adapter to put it out to the breadboard so I can easily get to things. And you see I have the same light sensor board, and for fun I hooked up an LED so I could turn it on and off from Linux. And the circuitry is pretty much the same. I've got the light sensor, I've got the same connections. Basically I'm passing power and I'm providing the data connections. So the hardware, not that hard, even if you're inexperienced. Let me talk about the data capture now. So, like I kind of mentioned before, I have these ESP8266 boards. I had one in my front bedroom, one in my back bedroom. Then in the dining room, I have my server, which is the Raspberry Pi. And on it, so there's a protocol called MQTT, which stands for like message queue, telemetry, transport, I think. And it's a publish subscribe protocol on top of TCP/IP. It's very lightweight. And MicroPython has a client library for it. And there's a broker that you can apt-get install in Raspberry Pi or any Linux system called Mosquito. So I can run a broker there and send messages over this. And then I have, on my Raspberry Pi, I've got this data capture app. And so I have a light sensor, the data capture app, and I want to write flat files. So that's all great. But if you look at kind of MicroPython, it doesn't have threading. And ideally, you want to use kind of event-driven programming, but if anyone's done that before, it can be messy and ugly. So this is some code that's doing some event-driven programming. It has callbacks all over the place. I would call this callback hell. And it's also kind of intermixing your data interconnections with handling like error situations and things like that. And the scheduling is sort of like, oh, something is done, an event is done. I need to reschedule the same event again to happen in 5 seconds or a minute or whatever. This really low level. In Python 3.5, they have this thing called async await, and it kind of cleans up some of the callback stuff, but it's still a little painful. So kind of motivated from this, I created a framework called ThinkFlow, and it's a domain-specific language for IoT event processing, runs on top of Python 3 or MicroPython. And it was co-created with Rupak Majumdar, who's at the Max Planck Institute for Software Systems. And so why do we create this? Like I showed you in that previous example, the code can be convoluted. And there's also kind of no standardization in the Internet of Things world for sensor APIs or adapters or transformations. It's all kind of really low-level stuff. And also, kind of, if I'm writing for the ESP8266 versus the Raspberry Pi versus something else, you're typically using different frameworks or whatever. And so it'd be nice to kind of unify some of that. So I'll give you a simple example of what some of the code looks like. So let's say I want to sample a light sensor, and I want to write that value immediately to a local file. And then every 5 samples, I'm going to take the moving average of the last 5 samples and send it off to the cloud somewhere using MQTT. So this is a graphical representation, and that's actually what that code, that page of code you saw 2 slides back, that's what it does. And so here's a graphical representation of the ThinkFlow code. You see I have an event scheduler. It's going to schedule a sample of the light sensor, say every 5 seconds. And then the data is going to, I have components to write to a file, compute a moving average, and send it to the queue. So this is what the actual code looks like. So these 3 lines of code do the same thing as the page of code on the previous slide. So you can see, basically it's all about connecting things. So I have a sensor. I want to connect it to the file writer so I can write it immediately. And then I have transduce is a step that can do a stateful transformation, in this case, moving average, and then connect it to the MQTT writer. Then finally, I schedule this to be sampled every 5 seconds. So this will run every 5 seconds, and pretty simple. So that's ThinkFlow. So I'm using that then in my project on the ESP8266 as well as on the Raspberry Pi. So this is all the code then I had to write once I kind of had the infrastructure in place. This is all I needed on the ESP8266. So what the code does is at the top, it's doing a bunch of imports. There's a sensor API. I basically took one that was written for Raspberry Pi and ported it to this board. And then set up some parameters. I want to connect to the Wi-Fi, instantiate the sensors. And then you can see that kind of the last 3 lines are really where I basically schedule it to sample every 60 seconds and then call the writer, which is going to send the message over the queue. And so that's all I need. And there's a special file in MicroPython called main.py. And anything you stick in that file, every time the system is booted up or reset, it'll run that code. So I just stick that code there, and then every time I run, it'll run that and do this. So even if I lose power or anything, when it starts up, it'll start sending the messages over to the queue. So this is the Raspberry Pi. I won't go through all the code on that, but the basic idea is I've got 2 things going on. One is I get events. I get basically at a low level, I'm getting a socket event saying that there's data that's coming from the MQTT broker. And I have to parse that data out and then write the events to a file. And I'm also directly sampling from my local sensor. Okay. So that was kind of the data capture phase. And so after running this for 6 weeks, I think for each room I had about 25,000 samples of data, sampling once a minute. And so now we can do data analysis on all that data. And like I said, I do this offline in a Jupyter notebook. It's very convenient for doing these kinds of things. And the files are in CSV. And I think it's one of the dirty secrets of Internet of Things. For all these time series databases and all this fancy infrastructure, I think a lot of data gets stored in flat files. But it is very convenient to work with. And at the end, we want to create machine learning models we're going to send back to run in the player. Okay, so this is what the data for one room in one day kind of looked like. If we graph it, this is using matplotlib to graph it. And yeah, the API was a challenge, and now I understand how to use it. But it's kind of one day's worth of data starting at like 9 p.m. and going to a little after 10 p.m. the next day. And what you see, first of all, you see the data is very noisy. And you also see there's gaps in the data. So that might be that the Wi-Fi network wasn't working, or one of my kids bumped the Raspberry Pi. That it happened at least a couple times. Shouldn't have put it on the dining room table, I guess. But anyway, so there you see a couple issues. Those are issues that I think are common for sensor data that in the real world you need to have your data analysis deal with. Some other things you might notice, you see it was on in the evening, and then all night long it's off, which I guess you would kind of expect. The light's off, people are sleeping. Then you see during the day, the next day, you see a couple spikes here and there. That's probably where someone comes in the room, turns on the light to do something, does whatever they're doing. Luckily, they turned the light off. They're not wasting energy. And then, so you see a spike there in the data. You see some ambient light as well. So, during the day, there's light that might be coming either from another room or from, from the window shade there. And there's kind of this other area kind of in the middle where it's up a little higher. And it's not clear if that's ambient light or probably more likely, there was a light on elsewhere in the room. So there's a little things we have to kind of infer from this data. It's not kind of cut and dry. And what we really want from our data analysis before we had to do the machine learning is we really want a sequence of the light went on at this time, it went off at this time, right? Not kind of all this messy data. So the first thing I did is I used ThingFlow to smooth the data out a little bit. So I can run ThingFlow in the Jupyter Notebook. And so you can see it got a little bit smoother there, got rid of some of the noise. There's always, when you're smoothing data, there's the question of how much smoothing do you want to do, because you might get rid of interesting artifacts of the data if you smooth it too much. But I really want to have kind of discrete values. I want to say the light was either 0, or 1. And so I think as an intermediate step, I'll map it as like 0. There's like 1, 2, maybe 3 or 4 levels of the light that you can kind of see if you kind of look at it visually. So what I did to kind of get it that way is I ran k-means clustering. So that's a unsupervised machine learning algorithm where you give it a bunch of data, in this case my sample values, and you give it a number of groups, and it's going to try to group the data into those groups to minimize the distance between the values in each group. And so I basically gave it that. I said, put it in 4 groups, and it actually seems to put it in 3 groups. Then I can sort the groups by the average or by the ranges of the data and plot it out. And so this is what I get. So it's much more discrete now. I have 3 discrete values, 0, 1, and 2. And so if you kind of went from that to that now. So then the last kind of data pre-machine learning step is to take this data and map it to 0 and 1. And kind of what I did for that is kind of looking at the raw data and knowing what I know about the room. I think that this kind of thing, this hump in the middle, I think that's actually someone turning on a light elsewhere in the room or from elsewhere in the house. So I'll treat that as the light being on. So when I do that, then I basically map everything from 1 or higher as on. And this is what I get. And so now we're at a point where we have time series data and we have on and off values for the light. So now let's do some machine learning. So the kind of obvious thing would be to do a supervised machine learning technique to create predictions for the light. So you could do regression to predict the value of the light, or classification to classify it as either on or off. And your features might be the time of day, the time relative to sunrise, sunset, because obviously the amount of light you see every day varies, and is also the history. I mean, one of the things I'd like to capture is you notice that in the real data that you see, sometimes the light's on for a long time, sometimes it's on for a short time. So we want to capture that information somehow. And your target value then is obviously whether the light was on or off. But there's some challenges with this. One is that what's really interesting is not so much every sample at every minute, but when the light went from on to off or off to on. So, and there were only, even though I had 25,000 data points per room, in each room there were usually only about 200 transitions over those 6 weeks. So that means I have a lot less data to work with than maybe I thought I had. The other thing is, the class sizes are different. If I want to make a prediction of the light for this, it's off, right? Because most of the time it's off. So that's the most accurate prediction. This is simple. The dummy classifier will work really well on that, but not so interesting to achieve my original goal. And the other kind of final issue with kind of traditional machine learning is that it's really a random process. I'm not trying to classify something really. I'm trying to create some random thing that has a similar pattern, but is different every time I do it. And And so I tried a few things, and I mostly got the light, predicting the light is off. I know a little more about machine learning now, and I think I can probably improve it, but what I think is kind of another good approach to this, which is what I use, is called a hidden Markov models. So a Markov process is a state machine, and it's a state machine where every outgoing transition has a probability associated with it. So if you look at, this is one from, I took this example from Wikipedia. You have it's sunny or it's rainy. Well, so if it's sunny today, there's a 90% chance of it being sunny again, 10% chance of it being rainy the next day. And if it's rainy, then it's 50-50. And so this is probably Sunnyvale, not Seattle in the rainy season. But, and the thing is, you notice the probabilities are determined only by the current state, not the history. That makes it a lot simpler. So in a Markov model, you're saying that if it's sunny, if it was sunny 20 days in a row, you still have the same 90% chance that it's going to be sunny tomorrow. It does, whether it was 90 days, 20 days, 1 day, or 50 days, it doesn't matter. Only the current state matters. Okay, so a hidden Markov model says, I don't know what the state machine looks like. All I see is the outputs. And so those their mathematical terminology, they call it emissions. So in our case, the emissions are the light values. And so in a machine learning world, what we want to do is say, given a sequence of emissions or light values and some number of states that I'm going to guess the state machine has, I want to figure out what that state machine is, or some approximation, basically the closest approximation I get. And then every time, once you have that state machine, it's all probability based, it's a random process. I can just play it any number of times I want and get predictions out of it. And so there's a library to do this. It was actually originally part of scikit-learn, and I guess they split it off at some point. And it's called HMM-learn, and it has a very similar API with fit and predict that scikit-learn has, so it's easy to use. And the problem with this approach, though, if you see, is it doesn't really account for the time of day or sunrise, sunset, or any of that. It's just replaying a pattern. So the approach I came up with to address this then was, I basically, looking at the data, I said, I'll split the day into 4 time periods. So I have one is overnight and up to sunrise, and then sunrise to a little bit before sunset, and then 2 early evening and late evening. And so that's determined by a combination of sunrise, sunset, as well as the, an absolute time there, 9:30. That was like usually when my kids went to bed. So I figured these are times when the light pattern is different, and I can basically separate the data and compute a different model for each time period. So here's kind of the training and prediction process then. So what I do then is I have all this data that I gathered, and basically for a given room, I build a bunch of subsequences for each time zone. So I have a particular time sample, and I figure out what zone of those 4 zones it's in. And then I keep on adding to my sequence until either I hit a gap in the data or I hit the next zone. And then I need to back up because I don't want to sometimes I might have a gap in the data. You don't know in the gap of the data if the light stayed in the same state or if it went on and off for 20 times. So what I do then is I kind of back up to the previous transition, and then I have some number of transitions in a set of samples that I kind of know everything that happened there, and they're all in one zone. So I can create a whole bunch of these, and then I can guess a number of states, and I guess 5. The reason I pick 5 is you would think 2 because the light's on or off, but like I said, I know sometimes it's on for a short time and sometimes it's on for a long time. So I figured you need at least 3, and just as a safety factor, add a couple more. And then, for each zone, I can create a hidden Markov model and call fit and give it all these subsequences I created of the data samples, and then it can do the predictions. And then when I want to run the predictions, I know a day is 24 hours. I figure out how many minutes, because I'm doing the samples at 1-minute intervals. How many minutes do I have in each zone? I just say if it's like 120 minutes, I ask for 120 samples from the predict method, and then it gives it to me. Then I stitch them all together and add timestamps in, and I have my predictions. So this is kind of what the predicted data look like for that front room. The upper left is showing you a week of data, and you can see it kind of went on and off every day at least once. and it has some short ones and some long ones. So it's pretty good. And you can see one room there, so it's off all night. That's the other kind of feature I want to make sure I reflect in my system is I don't want the light going on and off a lot in the middle of the night because that's not very realistic. So that's kind of a validation criteria. And so it's on, it's off all night, and it's on some during the day and into the evening, and you can see there's different intervals each time. So this is a pretty good simulation of if someone was in the house, what you would see. So now we're at replaying the lights. And what we see here is we have the Raspberry Pi, and we're going to take those machine learning models, copy them over. And then, so the Philips Lights has a bridge that you plug into your Ethernet network, and it's using the Zigbee protocol to control the lights. And we don't have to touch that part. We just have to use the REST API to do it. And we just have to say, okay, turn the light on, turn the light off, that kind of thing. And so I'll go into this. So there's a Python library called, I don't know how you pronounce that, Foo or Fui, but it's a Python interface over it. So I'm talking Python objects, and I don't have to deal with the REST API. Really convenient. So here's the pseudocode. So one thing I learned is you want to initially have a phase where you turn the lights on and off a lot, just to say, okay, did someone turn the switch off? Because the one thing the lights won't overcome, it can be the smartest thing in the world, but if someone turned the switch off at the lamp, it's not going to work. So you got to figure out all that stuff. So I have initial testing phase, and then it goes into this daily phase. And what it does, so from now until midnight, I predict the values of the light for the rest of the day. And and there's also, I should mention, there's a Python API to get sunrise, sunset for anywhere in the solar system, not just Earth, but I just looked up the latitude, longitude, and Sunnyvale, put in that in Earth, and then we're good to go. And so I can get, for that sunrise, sunset, I predict the zones, get all the values for the day. And then what I'm really interested in is I don't want to say every minute, oh, turn on the light, turn on the light, turn on the light. What I'd rather do is say, okay, I want to find the transition, so I just find all the transitions in the data. Then I can build an event list, which is a timestamp, a light ID, which is used by the API, so is it front room or back room, and then the state of the light that I want to set it to. Then I can take all the different predictions for the different lights, merge them together, and have a big event list for the day. So then for each event, I sleep to the event time and send the control message, and then I'll grab the next event and repeat the process. And then when you're done with that day, you wait till midnight, and assuming you don't have any bugs in your code, which I did the first time I did this, it will repeat that process again. So some parting thoughts, lessons learned. So end-to-end projects, I think they're great for learning. For me, it's kind of more motivating to work on something that has a complete real system as opposed to kind of a artificial homework problem. And you also kind of learn more about how the pieces fit together. And machine learning has a lot of trial and error involved, which I was fairly new to it when I started this. And that was one lesson I got out of it. And I think visualization is important both for machine learning as well as to understand the data, the sensor data in the IoT world. Because if you just had a bunch of numbers kind of making sense of that light data is really hard. And finally, the Python ecosystem is great for this kind of stuff. And in conclusion, if you want to reach me, here's how you can reach me. And all this stuff is online. ThinkFlow has its own page. All the code, if you want to try it out, all the Python notebooks or Jupyter notebooks are online. And there's also a hardware tutorial as well. Thank you.